I'm Daniel, and today we are now going to do question 3 of MAT 2022. So sketch y equals to x squared minus 1 to the power of n for n equals to 2 and n equals to 3. Now we all know the graph of y equals to x squared minus 1, right? Then we will have a y-intercept at -1, x-intercept at 1, and -1. If you square, it's like taking x to x squared. You take all the y coordinates and multiply them by itself. This means that all of the values will effectively be positive. And this will create this graph here. And similarly, for n equals to 3, you just warp the proportions near the x-intercepts, something like this. And Desmos graphing calculator does better sketches than me. So here you can see x squared minus 1 squared with the same intercept, x-intercepts, and a different y-intercept, this time it's squared. And you will have x squared minus 1 cubed, which will have -1 and 1, and then the same y-intercept as before. Without calculating the integral explicitly, explain why there is no positive value. The reason why there is no positive value such that this is 0, it's because the graph's always above 0. Therefore, the integral will always be positive. Take x squared minus 1 equals to 4, positive all the way around. X squared minus 1 to the power of 6, still positive, and so on and so on. If n is greater than 0 is odd, we will write n is 2n minus 1 and define this. Explain why such a number exists. It is because from 0 to 1, there will be a finite area in here. And then 1, you would say am. There's another finite area. And since the total area from 1 to infinity is infinite under this, am exists for each whole number, m is greater than 1. So for example, take this very strange graph, x squared minus 1 to the power of 101. As you can see, there's a finite area between x coordinates 0 and 1. And then you go all the way up here. I'm not bothered to do that because the graph so far, because we can still prove that there's a finite area. So let's find a1. We are going to find 0, a1, x squared minus 1 equals to 0. This means 1/3 x cubed minus x. You know the power rule for integration. You just, take out all the powers by 1 and then take 1 over the power times the coefficient. And since the coefficients are 1, this is easy. And sometimes you might see more complicated power rule, differential, integrals, and you might want to practice on these first and be very confident with them. Let's just call it a1. 1/3 a1 cubed minus a1 equals to 0. And this means 1/3 a1 cubed equals to a1. Therefore, we can take out a1 from all of these and end up with 1 here. So this means a1 squared equals to 3, and a1 equals to plus or minus the square root of 3. Since the negative solution is, well, negative, we can just rub out the entire negative solution. Prove that square root of 2 a2 square root of 3. Well, we are now going to solve part 6 in conjunction with part 5 because this is probably the simplest way to do it. So, when m goes toward infinity, we can just show that x squared minus 1, x squared minus 1, and then the x2 to the power of 2m minus 1. Now, what doesn't change? Well, obviously, the only two numbers which does not change, i.e. are idempotent in the reals, are 0 and 1. And when x squared minus 1 is 0, x equals to 1, only considering positive values. And when x squared minus 1 is 1, x equals to the square root of 2. And since these numbers don't change by any large number you put onto it, then this basically means that these two are the fixed points of every curve under this family. So, we use without proof this fact. The reason why this works is because now square root of 2 is our lower bound for all of these numbers. Therefore, we have answered part 6. This means that square root of 2 will be less than 0. And if we go higher up, we don't know the area yet because, well, the area is basically too high for us to compute. However, if we go back to the x squared equals to minus 1, 101, and we take y equals to 0 and y equals to 1, we see that it has the same fixed points, 1, 0, and square root of 2, 1. And therefore, we have solved this question. And so this question was basically an exercise on limits. Let's see how far you can take this number and then its power and then extrapolate it. However, we had just seen that there are several fixed points to a curve even when you change the power. This can be realized by using the idempotent properties of the numbers 0 and 1. Idempotence is used more in matrices, but idempotence of real numbers plays a part in this question. Well, see you